In an earlier lecture, we had analyzed state space models of a DC motor where the input was a voltage source. It generated an armature current which resulted in a back EMF, and the back EMF produces the angular displacement, the current results in the torque, and so on, and these were the governing equations. So what we saw here is that the control input, it directly so this is the voltage. It first affects the current, and this current in turn affects the speed of the motor. Okay, the speed can be directly controlled from V. So this is we called as a controllable system. We also saw how we can only measure the speed. I can't just go into the motor and maybe plug in a current measuring device and measure the current, but what I see is because I can measure the speed, so this is measured. Because due to this measurement and the relations between the mechanical and the electrical components, I can figure out what is the current in the DC motor, right? So on the other hand, now if I have a system, let's say I have x1 dot, x2 dot is 1 0 0 1, x1, x2 0 1 u. Okay, on the other hand, if I have a system which is x1 dot, x2 dot is 1 0 0 1, x1, x2 and 0 1 u, then simply split this as x1 dot is x1, x2 dot is x2 plus u, and what we see here is that the input affects x2, but there is no relation between x2 and x1. So this system I can only control x2 and not x1, which means the system is not fully controllable. Okay, so we can now ask ourselves a question of when is a system fully controllable. Okay, so hello and welcome to this lecture number 2 of week 11 of the course on control engineering. We'll start off with controllability analysis during this lecture. So our standard form of systems remains as it is. X dot is Ax plus Bu, where as usual X is a n-dimensional state vector, A is a n cross n matrix. Also write it as R n cross n. We also saw the notion of a state transition matrix e power at, and when u equal to 0, we could easily find the evolution of the system by just computing the state transition matrix together with the initial conditions. Okay, but what happens when we also saw a case when u was not equal to 0, but it was a constant. But what if u is a time varying signal? So let's start with this system in R, also a scalar system. The u is also a single input, and x dot equal to Ax plus Bu. So again the question is, what is x of t, or how does x evolve or respond, how does x evolve with respect to initial conditions, the control input, and these numbers a and b. Okay, so we'll just again the solution of x dot equal to Ax came via integrating both the sides and using standard tricks that we learn in calculus. We'll still do the same, right? So we just multiply both sides by e power at. We write down a series of steps here. I'll not read through those, but what we will end up is a system with solution x of t is e power at x naught. This was the same for the unforced system, which had u equal to 0, and then another term which was largely because of the control input to the system. Okay, so if I look at again a system of this form, simple LC circuit where, RL circuit where a voltage source drives the system with the output being the current. I just write down the state equations for that, di by dt. So I just start with so V equal to LdI by dt plus Ri, equivalently written in this form, resulting in a current expression which is like this. Okay, this is what we had also done earlier. How does this extend to systems which are when X is an n-dimensional vector or an n-dimensional state space, with A being a n cross n matrix? Okay, let's assume that for a moment that U is just a single input system. We just do the same thing, right? So the first term will correspond again to the system with U equal to 0, and this will neatly add on to the input term. Again, a series of steps will just lead us to something like this. Again, I'll skip those steps, but we'll keep in mind of what is happening here. Okay, so given so from this equation I can compute X via this expression, again where phi of t is e power at. So in general this is the state transition matrix. For LTI this takes the form of e power at. So once I compute X, I can just plug in the X here to compute what is my Y. Okay, so again I'll just present an example of what these things mean. So I have a system of the form x dot is negative 2 x1 plus u, x2 dot is minus x1 plus x2. Again, for simplicity I'm just taking u as 5, and with initial conditions of 2, 3. Again, I'll just write down, first step would be to find out the state transition matrix. You can do this with whatever method. The easier one would be to do with the Laplace transform, and then go on to compute the term which kind of sits here. Again, I'll skip the steps, but the end will look something like this. Again, what happens here, what is the steady state value, will not be of immediate interest. For now, we will do a lot of qualitative analysis of systems. This was just an illustration of how to go from a system which was just x dot equal to ax to finding solutions to x dot equal to ax plus bu. Okay, so with that, the first important concept we will discuss is that of a control system, is that of controllability. So I start with x dot is ax plus bu, y is cx, u can be a n-dimensional vector, but for the initial analysis we will assume that u is just a scalar without loss of any generality. That complicated or not very beautiful looking expression takes this form. So this is the solution to the system of equations. Okay, now we'll try to exploit this structure to ask ourselves a question: when is the system controllable? Okay, so a system is controllable at time t0, some initial time. We can also assume this to be 0. If there exists an unconstrained control signal, it can be as large as possible as long as it is bounded. That will take the state of a system from any initial state x0 to any initial state x final. Some initial state, some final state. Say I am moving from Chennai to Bangalore. That's my control. That's the initial state at time t equal to 0 is Chennai. The final state is Bangalore. So can I go from Chennai to Bangalore in finite time? We'll not really say what is that finite. The finite could be just 1 hour, you take an airplane. It could be 6 hours if you take a train, several more hours if you just want to jog to Bangalore, and so on. So we will not even look at the time, right? So it's not about, we will not put any constraint on the time. Okay. So if an input can be found, right? If there exists an input that takes every state variable from a desired initial state to a desired final state, the system will be called controllable. I should be able to go not only from Chennai to Bangalore, but maybe even Chennai to Pondicherry, or Chennai to Delhi, and so on. Okay. Then we will see how we can use this property to do some closed loop analysis. In the root locus or Bode, we did the dominant pole analysis. Can we have something equivalent of the dominant pole analysis here? Can I shape my root locus? What is the equivalent of that? What is the equivalent of shaping my root locus here when I go from an open loop system to a desired closed loop system with some performance specifications? Okay, so the definition only requires that the input should be capable of driving the system, and what trajectory it takes doesn't matter. It doesn't matter how I go from Chennai to Bangalore. As long as I can reach there, that should be enough. What trajectory I take, how fast I go, that we will be up for discussion in an optimal control course. Here I am just asking a question: can I do something? A binary answer, yes or no. So we'll deal with that qualitative property here. So what is an uncontrollable system? So if I take a circuit of this form, there are 4 resistances, each of the same value, which means that this VA and VB, or these points A and B, will be at the same potential. So if the capacitor has no initial charge, then the potential, then the drops at A and B are the same, and no matter how large control input we apply from here, we will never be able to drive the voltage to some desired voltage level. Okay. So the input has no effect over the voltage across the capacitor. The system is therefore not controllable, right? Just a very simple qualitative analysis can do this for us. Okay, I take another system, and where, okay, in this system what was happening was that the voltage across the capacitor doesn't move. If it starts with 0, it just remains 0. Okay, I'll take another example where I have a RC circuit. Both have same values of R and C. I just write down the equations, the standard KCL, KVL based equations. So what I see here is that, okay, let me just say R C equal to 1. So what happens here is that x1 dot is minus x1 plus u, x2 dot is also minus x2 plus u. Okay, if I just look at this equation in isolation, I can take or design a u which will take me, say, from x1 equal to, say, 1 to 100, whatever that number could mean, right? So this voltage, right, it can go from 0 volt to 100 volt, as long as I can buy an appropriate voltage source. If I look at this independently, x2 also can be driven to a voltage of, say, 200. But if I say, can I drive the system to, say, x1 is 100, x2 is 200 with help of u. Okay, so first I look at the first equation, I design some u, and say the u is, say, some u1. Okay. Now this u1 will drive x1 to 100. Now the same u is being applied here. Now can I use the same u to drive this to 200? The answer is no, right? Because I already fixed my u to u1, which will drive my x1 to 100. Now if I do the reverse, right, can I first go to x2 and design a u2 which will drive this to 200? The same u, can it drive this x1 to 100? That's not possible, right? So here all my controller can do is to drive x1, x2 such that both are equal. It cannot have x1 equal to 100 and x2 equal to 200. When I say a system is controllable, I should be able to control all the individual states to as much desired values as possible. So here, even though I can move the system from a non-zero voltage to some voltage, but I cannot move them independently. So these two will be at the same voltage. I cannot drive them to different locations. Okay. So this system is also not fully controllable. I can only go in some directions, but I am unable to go in all directions. Just like, say, if I have some kind of a car model where I can move in this direction. So can I start from here and end up somewhere here where only directions are allowed are I can just go forward and backward? No, right? What I would need additionally is a steering control also. Okay, so the car just with lateral movements is not fully controllable system. I need the steering control also to make it fully controllable. Okay, so I ask myself a question of how do we analyze this? So give me a transfer function. I was able to say whether the system was stable or not. I was also able to say a little bit about the speed of the response of the system. I also would be able to say the steady state errors, if any. Okay, so what we started off with, so I start with any initial time t naught. Let me say this is t0. I want to reach some final state at say some time t1. So without loss of generality, let me assume that my initial time is 0. Let me say that the final state is the origin. So if I were just to draw this in the x1, x2 plane, the problem means that I should be able to start from anywhere and reach the origin. And the converse problem is also true, right? So I should be able to go from origin to anywhere. So both problems will mean the same. Okay. So which means I start with my solution of the state equation. What is, so at x equal to t1, okay, so this is at t equal to 0. At x equal to t1, I am at the origin. So x equal to t1 will be the origin. E power a t1, so this remains as it is. I am just looking at what happens at t1 and what is here. So look at this expression. So of course 0 is known, e power a t1, this is a known quantity, initial condition is a known quantity, b and a again are properties of systems. So this boils down to finding like this is an equation, right, with an unknown is only u. Okay, so I will not here be interested to find what is the exact u, but to derive conditions under which u of t exists. For as simple as if I look at solutions to ax equal to b, I say unique solution exists only if a is invertible. That's all I would. I am not really interested at the moment in what is the exact u. First I ask myself a question, is the system controllable, or does a solution to this equation exist? Okay, I rewrite and things in a little better way. So I get x of 0 is something like this, or some expression like this. Okay, so what I would do here is to use a fact that I can expand e power at as something like this. Of course, I will not go to the derivations of this, but this should be easy to check. So in that case, what happens is this e power a tau. So I just have terms here. These are just the system properties, and the unknown now sits inside here. Okay. Now this alpha case, these are also known. I can compute this alpha case by the formula of e power at. Okay. So I call this as betas. So what results here is x naught is all of these sums times beta k, or I can write this in a nice matrix notation. Okay, you can just write this down by hand and check what is going on here. So I have now x naught equal to negative of c. C is just a matrix which I can compute. B is known, A is known, so I can always compute this matrix times some matrix B, and the U is sitting inside this B, right? In this beta via this. Okay, now when does a solution exist? This is known to me. This is known to me. I am just dealing with a single input, single output system. Beta is where my unknown sits. So I am looking at an equation beta times c is negative of x0. So beta will exist if and only if this c is invertible. Okay. So the complete condition for complete state controllability will be only when rank of C equal to n, which means the controllability matrix is invertible. Of course, here I'm assuming that U is simply this is just a single input system. Okay. So the first question of when is my system controllable translates to finding the rank of the controllability matrix. If the rank is n, rank of the controllability matrix, which comes from B and A, if that is n, then my system is controllable. The results can be extended to a system with m inputs also. I still construct the controllability matrix, which is n cross n m, and I still check for the rank condition. If the rank of C, now this is universal, right? If rank of C is n, or if I am able to find n linearly independent column vectors, then the system is completely controllable. Okay. So what is it? What is the definition, or what is the interpretation, that if the system A comma B is controllable, so I'll just write x dot equal to ax plus bu. I'll just call this as the pair AB is controllable, means that the dimension of C has full rank. So this is the test for controllability. That's a simpler test that we will use in this course. There are other tests. We will not go into those details. Maybe a more detailed course on linear systems can help you get there. Okay, so we look at systems again. Let me write this down in a little more detail. So I have x1 dot is x1 plus x2 plus u, and x2 dot is just 2. Okay, so what we see here is that u doesn't enter x2, not even through x1. So I compute the rank of the controllability matrix. So B and AB I compute 1 1 0 2 1 and a 0. This will be 1 and a 0. This is 1. This will be 1 and a 0. Okay, so this system is not controllable, right? This the second variable x2 is decoupled completely from the input. Okay, so on the other hand, if I look at a system which is of the form, okay, something like this, right? So here I write down the equations. X1 dot is x2, x2 dot is minus 2x1 minus 3x2 plus u. You see that u enters x2, but this x2 can also influence x1. Okay, and therefore the system, we can see intuitively is controllable, but the rank condition also agrees that C will have a full rank, and therefore the system is controllable. Here there is no direct or even indirect control of x2 either through the input or through x1. If it had a term corresponding to x1 here, possibly something would have happened. This is to x2. Okay, so what is happening? So let me start from here and try to derive the transfer function. So I do all the math, and what I see here is that I start with a system with n equal to 2, and I end up with a system which has only one pole, right? It doesn't have two poles. So what happens is that there is some pole 0 cancellation that happens, that results in only one pole for the overall system, right? So the pole as at x equal to 2 is uncontrollable, which means it cannot be influenced by the input u, right? So whenever a system is not controllable, that will show up as a pole 0 cancellation in the transfer function. Also intuitively you can think of it, if pole is cancelled, the control input can no longer influence the state of the system associated with that particular pole. And therefore, whenever I derive the transfer function, so this will be the transfer function of only the controllable part. I don't really get to see what happens is there any uncontrollable part in the system. What comes to me is just as 1 over s minus 1. So, the transfer function of a system is only the transfer function of the controllable part. We will do a little more formal derivation of this, but for now we can see loss of controllability means some kind of a pole zero cancellation. Now I can see the counter to that, a system which is fully controllable has two poles. There are no pole zero cancellation. The system started with n equal to 2. It has two poles, so there are no pole zero cancellations, and the system will turn out to be controllable. And now where the controllable canonical form fits in is, if you see any system associated with this structure will always be controllable. I mean, the A's could also be 0. I can simply have a system of x1 dot equal to x2, x2 dot equal to u, and check that this system is still controllable, and hence the name controllable canonical form. So we'll stop this analysis here, and next time we meet, we will look at how to use this property to design systems which will give us a desired response. Thanks for watching.